1995, a team of scientists achieved something that had been theorized for 70 years, but never observed. They cooled atoms to a temperature just billionths of a degree above absolute zero, creating an entirely new state of matter. At the center of this breakthrough was Wolfgang Ketterle, a physicist whose mastery of quantum mechanics would earn him a Nobel Prize and transform our understanding of matter itself. Born in Heidelberg, Germany in 1957, Ketterle grew up during a time when quantum physics was still revealing its mysteries. His fascination with the fundamental nature of reality led him to study physics at the Technical University of Munich and later at the Max Planck Institute. By the early 1990s, he had established himself at the Massachusetts Institute of Technology, where he would pursue one of the most elusive goals in physics. The quest centered on something called a Bose-Einstein condensate, a state of matter predicted by Albert Einstein and Indian physicist Satyendra Nath Bose in 1924. The theory suggested that if you could cool a gas of atoms to temperatures approaching absolute zero, something extraordinary would happen. The atoms would lose their individual identities and behave as a single quantum entity, a kind of superatom, where thousands of particles move in perfect unison. Ketterle's approach involved trapping sodium atoms using magnetic fields and then cooling them with precisely tuned laser beams. The lasers worked like optical molasses, slowing the atoms down by bombarding them with photons from all directions. Once the atoms were cold enough, he used a technique called evaporative cooling, similar to how a cup of coffee cools when the hottest molecules escape as steam. The coldest atoms remained, forming a condensate. What made Ketterle's achievement particularly remarkable was not just creating the condensate, but producing it in quantities large enough to study in detail. His condensates contained millions of atoms compared to the thousands achieved by earlier experiments. This allowed him to observe phenomena that had never been seen before. He watched as matter waves interfered with each other, creating patterns that revealed the quantum nature of the condensate. He created the first atom laser, a beam of coherent matter waves analogous to the coherent light waves in an optical laser. The implications of this work extend far beyond the laboratory. Bose-Einstein condensates have become essential tools for testing fundamental physics, from exploring quantum mechanics to simulating conditions found in neutron stars. They have applications in developing ultra-precise atomic clocks, quantum computers, and sensors that can detect the tiniest changes in gravity or magnetic fields. Some researchers believe they could even help us understand dark matter and dark energy, the mysterious substances that make up most of the universe. Ketterle's laboratory has continued to push boundaries, exploring how these quantum systems behave under different conditions. His team has studied superfluidity, a state where matter flows without any friction or resistance. They have investigated quantum phase transitions, the abrupt changes that occur when quantum systems shift from one state to another. Each experiment reveals new aspects of how matter behaves when quantum effects dominate. The recognition came in 2001 when Ketterle shared the Nobel Prize in Physics with Erich Cornell and Carl Wieman, who had created the first Bose-Einstein condensate just months before Ketterle's team. The prize acknowledged not just a single achievement, but the opening of an entire field of research. Today, laboratories around the world use the techniques pioneered by these scientists to explore quantum matter in all its strange and beautiful forms. Wolfgang Ketterle transformed theoretical predictions into observable reality, giving scientists a window into the quantum world. His work demonstrates how cooling matter to its lowest possible energy state reveals its most fundamental nature, where the rules of quantum mechanics create phenomena that challenge our everyday intuitions. Through his mastery of experimental technique and his ability to coax atoms into revealing their quantum secrets, Ketterle has shown us that matter, at its coldest and most controlled, behaves in ways that continue to surprise and inspire,